talk about the origin of a Smith chart. Now, back in 1939, Philip Smith, he devised a method, a way to map a complex plane into a graphical method to solve for transmission line problems. So we'll take a look at the complex plane. Now, in order to plot impedances on the plane, we use complex numbers in a rectangular form. So, and complex numbers just made out of real and imaginary numbers. Now, real numbers are just along this plane here. This is 0 here, and this is just positive numbers going this way and negative coming back this way. Well, what's this imaginary number? Well, mathematicians use the letter I for imaginary, but George Ohm, he used I for intensity or current, so we use the lowercase j for imaginary. And we say that's equal to the square root of -1. If you put -1 in the calculator and you try to do the square root of that, it's going to come up with an error message. You can't do it. What it allows us to do, though, is it allows us to rotate a phasor counterclockwise around this in this plane here, starting from this point here going around. So if you multiply by plus j, you wind up here, -1 over here, minus j down here, and plus 1 over here. It's just a way of allowing us to rotate this phasor around here. Okay, so let's try a problem here. We've got a 146 megahertz frequency coming in here. We've got a 50 ohm resistor, and then we have a 109 picofarad capacitor. So we know we're 50 ohms. We want to find our capacitive reactance here. So we just use this formula here, 2 pi frequency times the capacitance. So we plug it into the formula, and it comes out to capacitive reactance of 10. So to write our impedance in rectangular form, we just say Z is equal to 50 minus J10. Now, we go minus J10 because capacitance is down this direction, minus, and inductors are going to be up this way, positive J. So it's just 50 minus J10, and that's our impedance there. So we can plot it over here. So what we do is we take our real number first, and these are 10 ohms, 25 ohms, 50 ohms here. And then our imaginary number is coming down this way, and this is minus this way, and 10 ohms is here. So we just draw these two lines together, and this point right here is 50 minus J10. And that's our impedance, okay? Now, you can find your the actual impedance, if you want it in ohms. It's the length of this hypotenuse right here. So in order to calculate that, you can just take use Pythagorean's theorem, take imaginary number squared plus the real number squared, and you take square root that, and it actually comes out to 51 ohms. But we're going to use these in the rectangular form because it makes math a lot easier to add and subtract them together. You can multiply and divide, but to do that, we usually convert that to polar coordinates, and that's easy to do too. But for now, we're just going to use rectangular form, and that's what we use over here. So let's take a look at a feed line. Now, this is a typical feed line here. This one happens to be 50 ohms, and that's probably the most common type. This is RG8X and coax, and it has a impedance of 50 ohms. You buy it, it has 50 ohms in it. You can't change that. And it's the ratio of the amplitude of voltage and current of a wave propagating along the line in one direction with no reflections, okay? So a couple other things we have to know. This incident wave, that's a wave inside the cable going from your source out to your antenna, and it stays in the cable. And your reflective wave also stays in the cable going from your antenna back to your source. And anything that comes out is called the transmitted wave that comes out to your antenna. So now, if we put a signal in here into this 50 ohm impedance of this cable here, and it sees an impedance, doesn't see an impedance of 50 ohms out here at your antenna, some of the wave will be reflected back down. So your incident wave's coming out, and some of the wave gets reflected back down the line here. And when it does that, The incident and reflected voltage and current waves combine and result in phase and impedance differences that vary with distance along the line. And then they return to the original position every half wavelength. Okay. So if we want to plot all that on this chart here, there's a formula to be able to plot different impedances on here in the cable, but it's very difficult to do. So Smith came up with this way of doing it. It makes it a lot easier. So how he came from this to this, first of all this stuff on this side we don't want to look at. That's negative resistance. It's not going to happen in the feed line, so we can forget about that half. So this here is 0 ohms along here, and what he did, these actually go up to infinity. This one goes to infinity, this goes out to infinity. They just wrap them around in a big circle to infinity. So this circle here these are circles of constant resistance. Anywhere along this circle here, it's 0 ohms, okay? All the way out to infinity. So you got 0 here and 0 out here. Our next line right here, this one here, these vertical lines here, this happens to be 0.2 ohms. So here it is here, 0.2 ohms. And the same thing, it just wraps all the way out to infinity this way and down this way here, out to infinity over at this point here. Then we have 0.5 and 1 ohm here. Now, these are all circles of constant resistance, so anywhere along this line is 1 ohm. All along that line. Now, to get your lines of constant reactance, these are these lines coming out this way. Now these lines all go out to infinity. So he started out at infinity, and he just circled back all the way back to infinity. So he starts here. This upper side is inductive reactance here. He started out here, and he just took a circle and brought it all the way back to infinity over here. Okay. And this one happens to be 0.2 ohms. The next one is 0.5. Now, of course, this isn't drawn to scale, and you would have a lot more lines in here than this. But just for simplicity, I'm doing it this way. But all these constant reactance circles are all like this. And on the bottom here, this is inductive reactance up here, capacitive reactance down here, and these are tangent right here from infinity here. And all these just make big giant loops out here. Anything outside of the circle, the 0 ohms here, we don't care about. That's all negative resistance, and we don't care about that. We just want to know what's inside of here. So we want to plot this 50 minus J10 on here, okay? So here's 1 ohm here. Now 50 ohms is way down here, and it's going to be impossible to do anything with it. So what they want to do is they want to normalize it. So, most antenna feed lines are 50 ohms. So to normalize it, we'll divide by 50. So we have 50 here, so we divide by 50, and that comes out to 1 ohm, which is going to put us right on this 1 ohm circle here. And then this minus J10, we divide by 50, and that's going to come out to 0.2, okay? Now, the 50 is on constant resistance circles, so it's going to be around here. And these circles here, since we're dealing with a capacitor here, these are our circles of constant reactance. And this one here happens to be J minus 0.2, okay? Because we take our 10 ohms and we divide that by 50, and that gives us our 0.2, okay? So this point right here, this is our 50 ohms here, and this is our 10 ohms this way here, and that point right there, that's the same as this point right here. Now, we normalize that just to make it easier. So if you want to normalize it by a 70 ohm cable, you can do the same thing, just divide by 70. But we're dividing by 50, so this 1 ohm here becomes 50 ohms, and this 0.2 here becomes 10 ohms of capacitive reactance. So this is our point right here, and that's the same as that one right there. Now, what this does, if you take a compass and you draw a circle from this point right here through your capacitive reactance here, anywhere along this line here, the impedance is going to change, but your SWR, your standing wave ratio, and that just tells us how much power is actually getting out to our antenna. It's going to be the same. And we read it right here. So this is 1, this is 2, so that's about 1.5 ohms there. 1.5, or the SWR would be about 1.5, okay? And that's, now, this isn't to scale, and I don't even know if it's going to be 1.5, but the way it's drawn here, it looks like it. And 1.5 is pretty good. A perfect match would be 1, but 1, 4, and 5 is acceptable. So in order to do that over here, that would be very complicated. But so just by knowing the rectangular form up here, our impedance, we plot it down here, and it can give us our SWR right here. And there's a lot more things you can do with it, but that's just the basics of the Smith chart. Let's take a look at a real Smith chart. And here we are here. And we're going to plot our impedance of 50 minus J10 on here. Now we normalize that by dividing by 50, so that comes out to 1 minus J 0.2. Okay, so we take this one here. This is our constant resistance circle here. So we start there, and this arc here is 0.2. That's our constant capacitive reactance down here on the bottom. So we put our point right there. So this is going to be our impedance right here. Now, what we do is we take a compass, and you start from the center of the graph here, and you draw a circle through your impedance right here. And then when it crosses this resistance line over here, this actually gives us our SWR here. So we can see it just a little bit past 1.2 there. So that's our SWR. And another way to take your SWR is to go down to the bottom of the graph here, drop a line off the circle, and it crosses this graph down here, and it actually this is SWR here, the top number, and it crosses right through 1.2 SWR. So 2 ways to find your SWR. This is probably a little easier right here, but that's kind of the basic of a Smith chart. Thank you.